Okay, so another example. A gas turbine engine takes in air at 100 kilonewtons per meter squared, 16 degrees Celsius, and compresses it to 500 kilonewtons per meter squared at an isentropic efficiency of 0.84 or 84%. The air enters a combustion chamber and the combustion products leave at 490 kilonewtons per meter squared and 600 degrees Celsius. The turbine then expands the gases to 100 kilonewtons per meter squared with an isentropic efficiency of 0.88. And we're told that the engine produces 1500 kilowatts of power. We're asked to work out the air mass flow rate, neglecting the fuel mass flow rate. And we're told that if the calorific value of the fuel is 45,000 kilojoules per kilogram, and the combustor has an efficiency of 95%, what is the air to fuel ratio? And we're given some constants. Okay, so this is a pretty long question. Let's jump right in. So first of all, we have to look at what we were given. So we're given the pressure and temperature at the inlet. We just converted it to Kelvin. We're given the pressure at the pressure at the compressor outlet, but we're not given the temperature, so we're going to need to calculate that. We're given the pressure and temperature at the combustor outlet. Again, we just changed the temperature to Kelvin, and we're given the pressure at the engine outlet, but we're not given the temperature, so we're going to need to calculate that. We're also given the efficiencies. Okay, so first thing to do is calculate the temperature of the compressor outlet, and then we'll calculate the temperature of the engine outlet. So we're going to use this equation, which we've been using the last couple of examples. We just plug in the values. So T1 is 289, P2 is 500, P1 is 100, gamma is 1.4, and the efficiency of the compressor is 84%. When we do that, we get the temperature at T2 to be 490.2 degrees Kelvin. So the second part, we're going to rearrange this equation to get the temperature at the outlet, the ideal temperature. So we'll just plug in the values here. So we have 873 here. The pressure out here was 100 kilonewtons, and the pressure here is 490. So the input to the turbine nozzle is 490 kilonewtons. The output is 100 kilonewtons. And we're told that gamma for combusted gases. So we've air here, we've air and fuel in the turbine nozzle area. So the ratio specifically is changed. So that's 1.3. When we do that, we get an ideal temperature for T4 of 605 degrees Kelvin. But the turbine has an efficiency of 88%, and we want to get the actual temperature. So we can do that by multiplying both sides by the denominator here, and then bring the T3 across. Plug in the values. So T4 was 605, T3 was 873, and the efficiency was 0.88, and we get T4 to be 637 degrees Kelvin. Okay, so we have our two temperatures for the output of the compressor and the output of the turbine nozzle combination. Right, so the useful work is the work in the turbine minus the work in the compressor. So we're told that the useful work, the work on the turbine is the mass times CP gas, T4 minus T3, so T4 minus T3, and for here it's T2 minus T1. This is going to give me a negative value, so I need to take the absolute value of this. Okay. So an easy way to get the absolute value is just to the bigger value first. So this is going to be a larger one. So this is 873, and this is the 637. So that's going to be a positive value. Okay, so the mass times CP gas, when CP gas is 1.15 kilojoules kilogram, T3 was 873, T4 637, which we calculated. CP air was 1, we were given that. T2 is 490, which we calculated, and T1 is 289, which we were given. So when I multiply them out, I get that. So we have 70.4 M is equal to 1,500. The K's cancelled. This was 1,500 kilowatts, but this was in kilos and that was in kilos, so the K's just cancelled. So I get M to be 21.3 kilograms per second. So the mass flow of air is 21.3 kilograms per second. Just this clip down here. So this is the work on the turbine. So the turbine drives the compressor, and whatever left it goes out the nozzle to provide useful work. So our useful work is the total work from the turbine minus the work on the compressor. Alright, the last part of the question then. If the calorific value of fuel is 4,500, what is the air to fuel ratio? So the change in energy here, okay, is going to be equal to M times CP air T3 minus T2. Okay. So the air came in for the particular temperature, T2, it was increased to T3. So how did that temperature increase? Well, it was given some energy by burning of fuel. But the fuel that we burnt was done at an efficiency of 95%. So we'll just go back. So the combustion efficiency is 95%. So whatever we burn multiplied by 0.95 is going to be equal to this output. This is the energy out, I suppose. So I'm going to plug in the values. So the mass of the air was 21.3. CP air is 1 kilojoules per kilogram. And the change in temperature is 873 degrees Kelvin to 490 degrees Kelvin. So 490 in, 873 out. So Q then works out to be 8587 kilojoules. Okay. But we get that energy by burning fuel. So we burn jet A1. And the mass of fuel multiplied by the heating value of fuel gives us the energy out. So this 8587 is equal to the mass of fuel times the heating value of fuel. And we're told in the question that the heating value of fuel is 45,000 kilojoules per kilogram. So if I divide those, I get the mass of fuel to be 0.19 kilogram per second. Okay, so we have 21.4 kilograms of air going through. That should be 21.3. Okay, it's not a big change. We have 0.19 kilograms of fuel, so we divide both sides by 0.19 and we get 112 to 1. So the ratio of